power of concentration terms in an experimental is 1. So this is called as first order reaction. Rate with respect to concentration of reactant, that is ammonia, is 0. So that's why order is 0. So this is called as zeroth order reaction. The unit of a rate constant for first order reaction is per second or per minute or per unit time. Integrated rate equations. This is called as integrated rate equation for zeroth order reaction. The example of zeroth order reaction is metabolism of alcohol in rate versus concentration of the reactants. But now this graph indicates the concentration of the reactants versus time. Example of first order reaction is radioactive decaying. Hello students, welcome to Learn It. So as we already discussed, order of reaction is the power of concentration terms in an experimentally determined rate equation or rate law. So with respect to decomposition of hydrogen peroxide, the rate is equal to K into concentration of hydrogen peroxide raised to 1. So order is 1. So this is called as first order reaction. So let's take another example, that is reaction between hydrogen and iodine. So here the rate is equal to K into concentration of hydrogen raised to 1, iodine raised to 1. So the order of reaction is 1 plus 1, that is 2. So that's why this reaction is second order reaction. So let's take another example, the reaction between hydrogen and bromine. So here rate is equal to, with respect to hydrogen it is 1, with respect to bromine it is half or 0.5. So that's why the order is equal to 1 plus 1 by 2, which is equal to 3 by 2. So this reaction is called as fractional order reaction. So students should remember there is a fractional order reaction also. So let's take another one example, that is the decomposition of ammonia into nitrogen and hydrogen. So here the rate with respect to concentration of reactant, that is ammonia, is 0. So that's why order is 0. So this is called as zeroth order reaction. So zeroth order reaction, first order reaction and second order reaction. So rate with respect to zeroth order reaction is equal to rate is equal to K into concentration concentration of reactant raised to 0. So with respect to first order reaction, the concentration of reactant raised to 1, with respect to second order reaction, the concentration of reactant raised to 2. So let's discuss in detail about the zeroth order reaction. So as we already know, zeroth order reaction means the rate is equal to K into concentration of reactant whose power is 0. So that's why the rate is equal to K. Here K is called as rate constant for zeroth order reaction. When we plot a graph of rate versus concentration of the reactant for zeroth order reaction, we get a straight line because the rate is independent on the concentration of the reactant. So this is called as K, so which is y-intercept, because we already know that y is equal to mx plus c. Here x is 0, so that's why y is equal to c. So K, which is y-intercept. So unit for zeroth order reaction is moles per liter per second or moles per liter per minute or moles per liter per unit time. Let's look at first order reaction now. So as we already know that rate is equal to K1 into concentration of the reactant whose power is 1, which is the rate law for first order reaction. So here we can say that rate is equal to K1 into concentration of the reactant. So where K1 refers to rate constant for first order reaction. If we plot a graph of rate versus concentration of the reactant, then we get a straight line. So it means if we increase the concentration of the reactant, the rate will be increased. If we double the concentration of the reactant, the rate will be doubled. If we triple the concentration of the reactant, the rate will be tripled. So that's why we get the straight line. So with respect to unit of K1, the rate, we know that rate is equal to concentration divided by time. So concentration is indicated by moles per liter and divided by time means moles per liter per second. And with respect to concentration of the reactant, it is moles per liter. So moles per liter get cancelled. So that's why the unit of rate constant for first order reaction is per second or per minute or per unit time. So let's look at second order reaction now. So we know that rate is equal to K2 into concentration of the reactant bracket square. So K2 refers to rate constant for second order reaction. If we plot a graph of rate versus concentration of the reactant, we get a curve which is equal to y is equal to x square curve. So if we look at the unit, then we know that rate is equal to concentration divided by time. So that's why moles per liter per second, and with respect to reactant, it is moles per liter. So 1 moles per liter, another 1 moles per liter get cancels. So with respect to concentration of the reactant, which was square, so that's why moles per liter remains here. So it will go to this side, so it will becomes liters per mole. So here the rate at this part per second was remaining. So that's why unit is liters per mole per second or liters per mole per minute or liters per mole per unit time. The next important segment of this chapter is integrated rate equations. So here we are going to derive the integrated rate equation for zeroth order reaction, integrated rate equation for first order reaction. So let's begin with the zeroth order reaction. So as we know, rate is equal to K into concentration of the reactant trace whose power is 0. So that's why rate is equal to K. So with respect to differential rate equation is given by minus dr by dt is equal to K. Here minus sign indicates the reactant's concentration is decreasing. So when we rearrange, then minus d into concentration of the reactant is equal to K into dt. So upon integrating on both sides, we get minus integration of differentiation of R which is equal to integration of K into dt. So when we rearrange, integration of d into concentration of R is equal to minus K integration of dt. So which is going to give us the result, concentration of R is equal to minus Kt plus C. C is the integration constant whose value can be deduced by using the initial concentration. So when t equal to 0, that is in the beginning, then R is equal to R naught, where R naught is initial concentration. So that time the C is equal to concentration of R naught. So when we put the value of C into the above equation, then we get concentration of R is equal to K minus Kt plus concentration of R naught. So that's why when we rearrange, we get Kt is equal to concentration of R naught minus concentration of R. So when we rearrange the T, then we get K is equal to concentration of R naught minus concentration of R divided by T. So this is called as integrated rate equation for zeroth order reaction. So all the zeroth order reactions obey this equation. It means the reactions in which the rate is independent on the concentration of the reactants obey this equation. One of the example of zeroth order reaction is metabolism of alcohol in liver. No matter the amount of alcohol consumed, the liver always metabolizes the alcohol at a constant speed. Coming back to zeroth order reaction, if we further take the zeroth integrated rate equation for zeroth order reaction, and if we rearrange that is Kt concentration of R naught minus concentration of R, so we get the equation of Y is equal to Mx plus C. So if we plot a graph of concentration versus time, then we get a straight line where y-intercept is R naught, that is initial concentration, and the slope of this graph is minus k. Students must remember that before we discussed a graph of zeroth order reaction, which was a rate versus concentration of the reactants. But now this graph indicates the concentration of the reactants versus time. In the similar manner, let's discuss the integrated rate equation for first order reaction. So as we know, rate is equal to K into concentration of reactant, whose power is 1. This is the rate law. So rate is equal to K1 into concentration of reactant. So here K1 indicates the rate constant for first order reaction. So we know that rate is equal to minus dr by dt. So that's why minus dr by dt is equal to K1 into R. So after rearranging, we get minus dr by concentration of R is equal to K1 into dt. Integrating on both sides, so we get minus integration of d into concentration of R divided by concentration of R is equal to integration of K1 into dt. So which is going to give us, so if we rearrange, so integration of 1 by R into d into concentration of R, which is equal to minus K1 into the integration of dt. So we know that integration of 1 by concentration of R into d into concentration of R is equal to ln or log to the base E of concentration of R, which is equal to minus K1 into T plus C, where C is the integration constant. So the value of integration constant is calculated by taking when T equal to 0, R is equal to R naught. So which gives initial concentration. So that's why C is, we get ln into concentration of R naught is equal to C. So if we put this value in the before equation, we get ln concentration of R is equal to minus K1 into T plus ln of concentration of R naught. So when we rearrange, we get K1 into T, which is equal to ln of concentration of R naught minus ln of concentration of R. Logarithmic relation, that is ln m minus ln n is equal to ln m divided by n. So we get K1 is equal to 1 by T ln of concentration of R naught divided by concentration of R. So this is the integrated rate equation for first order reaction. So let's discuss this integrated rate equation for first order reaction further. So we'll take K1 is equal to 1 by T ln of concentration of R naught divided by concentration of R. So if we remove the ln and if we want log, then we need to multiply it by 2.303. So K1 is equal to 2.303 divided by T, log of concentration of R naught divided by concentration of R. So when we rearrange, we get K1 into T is equal to 2.303 into bracket log of concentration of R naught minus log of concentration of R, because we know logarithmic relationship. So K1 divided by 2.303 is equal to log of concentration of R naught minus log of concentration of R. So when we rearrange, we get log of concentration of R on the left side, which is equal to minus K1 divided by 2.303 into T plus log of concentration of R naught as it is. So this resembles the equation of straight line, that is y is equal to mx plus c. When we plot a graph, that is log of concentration of R versus T, we get a straight line with a y-intercept, that is log of R naught, which is having a slope minus K1 divided by 2.303. So students should remember that before we discussed about the first order reaction, in which the graph was rate versus concentration of the reactant, which was a straight line passing through the origin. But here it is the log of concentration of reactant versus time, which is a straight line having negative slope whose value is minus k by 2.303 with a y-intercept of log of concentration of R naught. One example of first order reaction is radioactive decaying of a substance. Similarly, if we take the second order reaction, the reaction can be given by rate is equal to K2 into concentration of reactant bracket square. Then the integrated rate equation for second order reaction will be 1 by concentration of the reactant is equal to K2 into T plus 1 by concentration of R naught, that is initial concentration. When we plot a graph of 1 by concentration of R versus T, we get a straight line having a positive slope, that is my K2, and y-intercept is 1 by concentration of R naught.